Great. So thanks a lot, Ariane, for the kind invitation and for organizing this event. So I will follow up on a little bit on what Marco introduced. I will look at this notion of beyond diagonal RIS, which is an emerging form of actually surfaces that provide additional degrees of freedom to do beamforming, sensing, computing, and so on. So I would like to thank a number of colleagues here. You see at the bottom of the slides, this is a lot of work done with especially my PhD students and postdoc at Imperial, Matteo, Hongyu, Yumeng, Shampu, and Yang, but also colleagues around the world. Right, so you're all familiar with RIS. This is not a new topic. It's been there for now quite some time, also called IRS. Essentially, you have a large number of passive reconfigurable elements that you embed within the environment, and you can engineer the channels thanks to that by having the RIS acting as a form of smart mirror. And this is actually an area that is studied in various communities in wireless, but also in optics, in physics. People do this also in sound or in sound processing. And you can use that for various applications in communication, sensing, in localization. You could do this in wireless power transfer as well. Now, one thing that is important is that those RIS are not limited to, sorry, I cannot move the slide. Yes. Those RIS are not limited to do just engineering the channels. Sorry, so they're not limited to just engineering the channels, as Marco often mentions in terms of making a smart radio environment, but they can do more. And so indeed, as Marco mentioned, you can do some form of processing and computing. It's a little bit the directions where the community goes. And so there's been a lot of actually various work that have shown that you can use RIS to have a form of programmable metasurface, to do some form of modulation directly in the analog domains, or you can do some form of computing, for instance, here when you do stacked intelligent metasurfaces, or actually use these programmable AI machines to have additional benefits than just beamforming. And the whole benefit of that, of having those intelligent surfaces that potentially embedded within base station, is to depart from conventional old digital-based processing and therefore decrease the power consumptions and improve the latency of processing and computations. Now, in all those areas where you use RIS for a smart radio environment to shape the electromagnetic environment, or actually you embed them within a base station to do some form of alternative to hybrid analog digital processing, or you want to go more towards computation, there are really two important challenges. The first one is how you model those RIS so that actually they're physics compliant, but also ideally they actually are compliant with information theoretic models so that they are tractable and useful for communication engineers. And the second challenge is how you design those RIS, and ideally in an optimal way so that you can really exploit all potential benefits of those RIS. So I will not go into both challenges here today because of limit of time. I will primarily focus on the optimum RIS architectures, and I will touch upon a little bit about the physics compliant models. So, but the physics compliant models, it's a very complicated area, and it's not a new area. So the whole area of electromagnetic information theory is actually an area that exists for a very long time. And so our Nobel Prize winner in the group at Imperial, Denis Gabor, actually was one of the fathers of actually trying to really merge information theory and electromagnetism. And so what we do here in this context is try to use multiport network theory to bridge electromagnetism and information theory. And so this multiport network theory, again, is not a fundamental new theory because it's been used in MIMO communication before, but it's very helpful in the context of RIS and future wave domain manipulations. And that really acts as a bridge between electromagnetism and information theory because it enables you to really model in a systematic way by being able to identify a number of assumptions and really identify the validity of each of those assumptions. So multiport network theory relies on what we know in microwave theory using Z parameters, so impedance parameters or admittance parameters, Y, or actually scattering parameters, S. And they relate essentially, they provide a relationship between the impinging waves on a given port and the reflected wave on that port. And so if you can model, for instance, a RIS or MIMO systems or stacked intelligent meta surface using this multiport network theory, where actually on any ports in your systems, you try to relate the impinging and reflected wave. So this is actually two examples where you could use multiport network theory. Here you have a smart radio environment, you have a transmitter, a receiver with multiple antennas, and you have a RIS with multiple elements. And what you try to do there is to characterize the relationship between the voltage at the receiver as a function of the voltage at the transmitter. And you can find actually this channel matrix that relate the transmit voltage to the receive voltage, and this channel matrix will be a function of the scattering matrix or the impedance matrix or the admittance matrix of the reconfigurable intelligence surface or the microwave networks of the RIS. And so what it enables you to do is to really characterize this channel matrix as a function of theta, and to do this in as much as possible physics consistent way. You can do this for SIM as well, but then your relationship between your voltage at the receiver and your voltage at the transmitter is still through a channel matrix H, but this channel matrix H is now a function of the scattering matrix of those L layers of RIS that you may have in your SIM. So this is possible. I will not go into all those details, but that gives you a channel matrix H that is actually can be relatively complicated because it will include any form of mutual couplings that you have in the system, any impedance mismatch, and any potential reflection that you have between those layers. The fact that you may have unilateral or specular reflections in the system. So there are a number of actually assumptions or phenomena that you can really capture into the systems. Now, if you make a lot of assumptions, you end up with these channel models that people are very familiar with in communications, where you say, if I have a transmitter, I have a receiver, and I have a RIS, essentially I would say that my channel matrix is a direct path, so HRT. I have a channels HIT here between my transmitter and the RIS. I have the scattering matrix of the RIS, theta, and then I have the channels between the RIS and the receiver. And so we're all familiar with this model. It's very important to keep in mind that this model holds under a number of assumptions. And some of them are you have perfect matching at all the elements, all the ports in your systems. You have no mutual couplings anywhere in the systems. You have unilateral approximation. That means actually your transmitter and the receiver are sufficiently far away from each other. So that's an assumption that would definitely not hold when you have SIM, because all the elements are very close to each other. So, and you have no structural scattering, so you have no specular reflections on the system. So if those assumptions are valid, then actually this channel model is relatively accurate, right? So in the sequel, I will use this model as much as possible, but sometime I will depart from this, and then I will go back into the multiport network theory. Now, this theta is very important. So this is often called phase shift matrix in the RIS literature, at least in the communication literature. More generally speaking, this is what is called a scattering matrix. So it really relates the impinging wave and the reflected wave on the RIS. And so I will use that terminology later on because this is a much more common terminology in microwave theory. But what is important in RIS is that this theta is completely reconfigurable. And this is really the whole benefit of RIS. So it's being able to change the circuitry of the RIS such that your theta is then reconfigurable. So the main question I want to address in this talk is how do you actually design this theta? And therefore, how do you design the corresponding impedance network architecture that is hidden behind a RIS surface. So the classical way of doing it, and we see in most papers, is this diagonal RIS. So what that means is that you have a large number of elements, and each of those elements can be essentially modeled as a port connected to a self-impedance. And this impedance is a tunable impedance. And so by controlling Z1, essentially you control the way the wave impinging on this element 1 will be reflected by element 1. What do you see in these architectures here is that all those elements are disconnected from each other. So the element 1 is not connected to element 2, not connected to element 3, not connected to element 4. Right, so any wave that is impinging on a given element will be reflected by that element. And so what that means is that mathematically, that leads to a scattering matrix that relates, again, the reflected wave to the impinging wave. This scattering matrix will be diagonal. And if you have a lossless system where all the energy that is impinging will be reflected by the RIS, then these diagonal elements will be of magnitude 1. That means actually you have energy conservation. So what you do, you control the phase of those diagonal entries. So the beyond diagonal paradigm is saying, well, can we essentially exploit potentially all elements of this scattering matrix or this phase shift matrix? So there are some zero element here, but can I actually make use of that? And so this is why now I have a scattering matrix where I have potentially non-zero entries everywhere here. I can exploit the diagonal element, but I can also exploit the off-diagonal element. And so what that means physically, it means that now the wave impinging, for instance, on port 2 here may be reflected by port 1. So that means actually I will have now interconnections between all those elements. And those interconnections will be tunable or reconfigurable. So what that means is that the wave now impinging on a certain port will actually flow through the entire surface before being radiated by the surface, or actually, so anything that is impinging on a certain port actually comes for actually a linear combination potentially of waves that is being impinging on different parts of the surface. And so the main question is, okay, what kind of architecture can you come up to do that? Why would you do that? And when does it make sense to do that? Right, so I will start with reflective case. So here I have just a surface, a RIS. I have a transmitter and receiver, and they're located on the same side of the RIS. So the wave would be completely reflected by the RIS. So classical one, the diagonal RIS, you have the scattering matrix is diagonal, as I said before. And so there, the wave impinging on the element 1 will be entirely reflected by element 1. And you note that the scattering matrix theta is actually symmetric. So it's a diagonal matrix, so naturally symmetric. And it's unitary. So it's a unitary matrix. And so that means actually it's a lossless system. So how many elements you need to control here? You have, if you have Ni reconfigurable Ni element in your RIS, then you need to have Ni reconfigurable impedances. So the same number of elements as the number of impedance. Right. So I will show you a few examples of BD-RIS. So the first one is this, what is called fully connected. So now what that means is I have Ni elements in this RIS, and I connect them all together. So there is direct path between any two elements of the RIS. And so what I need is now I have the number of impedance to control is roughly Ni squared. So the number of impedance to control grows quadratically with the number of elements I have in the RIS. Now this kind of RIS would have a scattering matrix that potentially could be symmetric. And the reason why we have a symmetric constraint here is to make the RIS or the impedance network of the RIS reciprocal is actually much easier to implement in practice. And it would have to satisfy this unitary constraint again that I mentioned earlier to be lossless. But the entries of this theta will not be necessarily just diagonal entries. I will have off-diagonal entries as well. And so what's the benefit of doing that? The first benefit is that I can not only adjust the phase of the impinging wave, but I also adjust the magnitude, because what is reflected by a certain element is not necessarily what is being impinging by that element, but is actually a linear combination of what comes from impinging on element 1, but also impinging on element 2, and then flowing through the surface and radiated by port 1, from port 4, from port 3, and so on. So that enables you this controllability of phase and magnitude of the impinging wave. Now, you may argue if your number of elements grows, then the number of impedance to control grows also very large. And this is a challenge, right? So you can come up with other architectures, and this is actually what is called a group connected. So now you split your number of elements into groups. So for instance, here I have 8 elements in my RIS, but now I actually divide it into 4 groups, where in each group I have 2 elements, but they're interconnected with each other. So there I have then a scattering matrix theta that is block diagonal, and each block is actually the scattering matrix of the corresponding group. And so each of those blocks here would actually achieve, or would be potentially reciprocal, or have a symmetry constraint to have a reciprocal circuit, and would have actually a unitary constraint as well to be lossless. So that would reduce the number of actually impedance to control. And so you can change the group size. So here actually 2 different examples. You can change the group size to actually then change the flexibility in the way you manipulate the waves. Now, I mentioned earlier you can control amplitude and phase. So that gives you actually a performance enhancement in terms of received power. So now if I have, let's say, a single transmit antenna, I have a single receive antennas, and I have a RIS somewhere, what I'm trying to look at is how much power can I actually captures at the receiver and antennas thanks to the presence of this beyond diagonal RIS. And so what you can see here is that in red you have a diagonal RIS with no interconnections. As you increase the number of interconnections, you have a group size of 2. So you have, for instance, 64 elements in your RIS. You have 32 groups with group size of 2. Or you have here 16 group of group size of 4. Or you have a fully connected RIS where you have all elements are connected. You see that the received power is increasing as you actually increase the number of interconnections that you have within your RIS. And you can show this mathematically, that if you have a SISO system, you can have a fully connected architecture will give you 60% higher received power than if you have a conventional diagonal RIS, but that comes at the cost of having a larger number of impedance to control. So with group connected, you decrease your received power gain, but you decrease also the number of impedance to control. And so intuitively, you can relate this to what we do in MIMO. In MIMO, you're familiar with equal gain combining and maximum ratio combining. Well, you can think of diagonal RIS as a form of equal gain combining. You only play on the phases of your scattering matrix. Similarly, what you do in equal gain combining. With beyond diagonal RIS, you play on the magnitude and the phase. So this is actually reminiscent of maximum ratio combining. And this is the reason why beyond diagonal RIS is actually optimal. And you can show that if you want to, whether you can increase the power gain beyond what has been achieved by these fully connected architectures, you cannot. Because the beyond diagonal RIS achieve the upper bound on the received power you can achieve. So that means actually beyond diagonal RIS is optimal, achieve the upper bound, even in the simplest case where you have a single transmit antenna and a single receive antenna. So that means actually if you go to more complicated systems, the beyond diagonal RIS will be also needed to achieve the upper bound on the performance. So second benefit is boosting received power. Consequently, you actually increase the rate and some rate if you have a multi-user systems. So this is an example of gains when you have now a multi-user MIMO systems that is added by a BD-RIS. So you have 4 transmit antennas that serves 4 users, and you edit by beyond diagonal RIS. You optimize jointly the multiple access schemes or the multi-user MIMO precoding schemes and the beyond diagonal RIS together. And what you see here is that the sum rate enhancement that you have compared to conventional RIS becomes very significant. You go from 8 bits per second per hertz to 14 bits per second per hertz. And the reason for this is because you have much higher wave manipulation flexibility and way to actually manage the interference that you have within the networks. And that gives you this very big boost and an increase of performance in terms of sum rate. So you have not only a gain in terms of power level at each of those elements, at each of those users, you have an SNR increase or SINI increase, but you have a better way of managing the interference in the systems. So you can have other benefits. This is actually channel shaping when you have a MIMO or RIS-added MIMO system. So you have multiple transmit antennas, you have multiple receive antennas. And what you can show is that actually you can actually now shape the distribution of the eigenvalues of these MIMO systems. And this is actually, for instance, illustrated here. You have two transmit antennas and two receive antenna systems. You have two eigenvalues in your systems. And this is your Pareto frontier between those two eigenvalues. So you can evolve here on this boundary with diagonal RIS. If you have beyond diagonal RIS, you have more flexibility in shaping the distribution of the eigenvalues. So you actually enlarge the Pareto frontier between those two eigenvalues. And so what that means is actually that has a benefit in MIMO system because it enables you to achieve higher degrees of freedom, a higher multiplexing gain at lower SNR. So you can activate multiple streams transmissions at lower SNR than if you have a diagonal RIS. So that's the benefit of being able to shape the distribution of eigenvalues in MIMO systems. And that's really the benefit, one additional benefit here of beyond diagonal RIS. Okay, so let's move on. You can then do other things. You can have a hybrid case. So if you take my group connected RIS here or beyond diagonal RIS, I have two groups. Now imagine I take this antenna 1 and 2, and instead of facing the same side of the RIS, I bend them so that they actually face opposite sides. And so what you get is now two panels here that is reminiscent of what is called star RIS, similarly transmit and receive. And so your beyond diagonal RIS here is actually an enabler of a star RIS. And a star RIS here is actually a form of group connected beyond diagonal RIS with a group size 2. And this is what you see here. This is actually a star RIS. But you can come up with other architectures to have this hybrid transmit and reflect. You can have here a simple star RIS architecture. You can have actually architectures where actually the elements are interconnected with each other. So element 1 here would be connected with element 2, or element 1 could be connected to element 4, and so on. So you can shape the interconnections so that you can increase the wave manipulation flexibility. And that gives you a higher performance gain even in the hybrid mode. So this is an example here again. This is a multi-user system, multi-user MIMO systems that is added by a hybrid beyond diagonal RIS, where actually you can reflect and transmit. You have conventional star RIS here at the bottom, and you see the performance gain that you have as you increase the number of interconnections that you have within your beyond diagonal RIS. And again, that gain comes from the higher wave manipulation flexibility that is coming from the interconnections. Right, then you can go one step further. You can say, well, instead of having two sectors, so two panels connected to each other, you can have multiple of them. So here I have, for example, a multi-sector hexagonal shapes. And so a wave impinging on one of those sectors will be reflected by that sectors, but actually the wave will flow through and then illuminate users actually in different parts of this 6-sector deployment, for instance. And so the benefit of that is that now each of those sectors could be highly directionals. So you could enable a fully 360 coverage, but in each of those sectors, you have highly directionals coverage. So that's very beneficial. And this is an example of sum rate performance in multi-user case. In red is when you have this kind of BD-RIS with 2 sectors. In blue is when you have BD-RIS with actually 6 sectors. So you increase the sum rate even further because you enable to have highly directional transmission, but at the same time full coverage across those 360 degrees. And this is enabled because the energy can flow through the surface across those 6 sectors. Right. Now, I gave you a few architectures now of beyond diagonal RIS. So you have the diagonal RIS, that is a particular case, but then you have the fully connected, the group connected, you have this hybrid mode, you have this multi-sector. An interesting question that arises is, what's the optimal way of actually interconnecting all those elements? And so what you can notice is that the beyond diagonal risk actually can be formulated by a graph. And so when you have a diagonal risk, you don't have any interconnections within your risk. So actually you have an empty graph. If you have a beyond diagonal risk where you have a fully connected architectures, where you have connections between any two ports, you have actually a complete graph. But then you can actually turn off some of those interconnections and you will end up with a corresponding graph that could be, for instance, acyclic or with a forest structure, for instance. Or actually you can have a connected graph where you have a path that goes across all the elements. But the question is, what's the best architectures? And so the one you would like is the one that achieves the same performance as if you have the maximum number of interconnections, but you would like to have this with the least possible interconnection. So you want to have the same performance as this bottom one, but with the least number of interconnections. And what you can show is that the optimal architecture is actually what is called tree. It's a tree-connected BD-RIS. Is actually a BD-RIS whose corresponding graph is connected and acyclic. And this is what you have here. You have connected because any element is connected to other elements, but you don't have any cycle in this graph. So that will give you the architecture that will give you the same performance as a complete graph, but with the smallest number of elements to reconfigure. And this is very important because that shows you that you can have actually relatively low complexity of BD-RIS that achieve the optimal performance. And so I showed you earlier the gain in terms of SNR gain or power gain. So the black one is now achieved by two types of architectures. Either you have a fully connected RIS where you connect all elements to each other with a direct path, or you have a tree-connected RIS. And those two architectures achieve completely different complexity. The fully connected will have a number of impedance to control that grows quadratically with the number of RIS elements, while the tree connected will have actually a linear increase in the number of impedance to control has a linear increase with the number of actually elements. So actually the gap between those two in terms of complexity is very huge, and you see it here, the circuit topology complexity that grows quadratically with the number of RIS elements when you have a fully connected RIS. If you have a tree-connected RIS, it grows linearly with the number of elements. So the gap between those two is actually very significant in terms of complexity reductions, but they achieve exactly the same performance. Right? So example of tree connected could be here. You have a path graph where actually between any two elements you have an interconnections, or you can have a path graph or a star graph where one element is connected to all the other elements. So those two different actually tree connected BD-RIS would achieve the same performance, but they would achieve, importantly, much lower complexity than if you have a fully connected RIS. So this is very important because that tells you that you can achieve low complexity but high performance BD-RIS architectures. And this is actually the Pareto frontier between performance and complexity. The lowest performance and lowest complexity is achieved by diagonal RIS. The highest performance and highest complexity is achieved by a fully connected beyond diagonal RIS. But you could achieve the same performance as this one with a tree-connected RIS. And so, for instance, here you have 64 elements in your RIS. Here you need over 2,000 impedance to control. In the tree-connected, you have 127 impedance to control, but you achieve the same performance, right? And if you want to further decrease the complexity, then you can involve on this part of edge here, and this is achieved by this called forest-connected RIS. It's actually a form of group-connected architectures where in each group you have a tree-connected BD-RIS. Right, so this gives you actually, now we can characterize the Pareto frontier to that really fundamental trade-off between complexity and performance. Now there's a number of challenges to address with BD-RIS. One of them is channel estimation. I will not talk too much about this, but so far you need to actually come up with tailored channel estimation method for BD-RIS. And one of the challenges is actually the overhead of channel estimation grows with the number of interconnections. This is actually a challenge that needs to be addressed. But you have other benefits. And this is an example. So far, I told you that all what has been done is continuous space optimization of those scattering matrices. Now, in practice, you would have discrete value impedance networks. And so the question is, how sensitive is a BD-RIS to the number of bits that you have for controlling each impedance? And interestingly, you have here the receive power versus the group size. So here you have actually a diagonal RIS. Here you have a fully connected RIS. And what you see is you have an increase in receive power when you have continuous space optimization. This is not new. We know this already. As you increase the number of interconnections, you have increased the receive power. What is more interesting is those other curves here that shows you how the receive power scales with the number of bits that you have for each of those impedance or tunable impedance. So if you have 1 bit, you have quite a big loss if you have a diagonal RIS. But if you have a BD-RIS with sufficiently large number of interconnection, you see that 1 bit is actually sufficient to come very close to the optimal performance. And so what that means is that with beyond diagonal RIS, you have maybe more interconnections, but each tunable impedance could be cheaper because can be realized with just 1 bit resolution. Right. Then you can have other issues. Mutual coupling is very important. So the model that I showed you does not hold mutual coupling, the conventional model. So you have to go back into multiport network theory to capture mutual coupling. And what we can do that, and what we can show is that if you actually pack the element closer to each other, for instance, here you have lambda over 4 spacing between elements, then the gain of having interconnections between beyond diagonal RIS is increasing. And so in other words, having interconnections helps you to actually have a more compact deployment of your RIS. And the reason for this is because the interconnections act as a form of artificial coupling between the elements, and they enables you to control the physical mutual couplings in a much more efficient way. Right, then you have other issues to consider. You may have losses between those interconnections, so this needs to be modeled using transmission line theory. This can be done, and what you can show is that if you have a localized RIS where the inter-element spacing between those RIS elements is small, then the loss are not so significant. If you have a more distributed RIS deployment where the interconnection is actually much longer, then actually you may have a more significant impact of actually those losses, but you may have also some benefit. I will not go into too much details, but here you show that you can have orders of magnitude gain of having BD-RIS in distributed deployment, but you have to be careful about the losses that you may have in this setting. Right, then you can have other problems, wideband modeling. So each of those tunable elements would have now a frequency selective behavior that needs to be captured when you do actually your optimization of your BD-RIS, especially when you have wideband systems that operate maybe at millimeter wave frequencies. And if you capture the frequency selective behavior, then actually you can have additional performance benefit of BD-RIS by having those interconnections. Right, then I will touch upon a few other, I think, useful cases. So the first one is the SIM, and how SIM could be implemented using this beyond diagonal RIS. And so what has been shown theoretically is that if you have a SIM architectures with a transmitter, with multiple layers of RIS, transmissive RIS, and then you have a receiver, what you can show is that the optimal way of doing beamforming is actually achieved by having a single layer of transmissive BD-RIS. So you don't need to have L layers of RIS. You can have a single layer of beyond diagonal RIS. And the reason for this is because this channel model here is purely linear. It essentially has a non-diagonal structure that would then tackled directly by a beyond diagonal RIS. So you can have one beyond diagonal RIS based on 3 connected architectures, and that will give you a number of elements to control that is equal to 4n-1, where n is the number of elements you have within 1 layers of RIS. If you have implement this with multiple layers of diagonal RIS, you have 3n multiply by the number of layers. So even if you take 2 layers of diagonal RIS, you're going to have a number of elements to control with this SIM with 2 layers that will be higher than if you have just 1 layer of 3 connected BD-RIS. So what that means is that not only BD-RIS will give you the optimal beamforming gain, but it will do this with the lowest circuit complexity because you have the lowest number of tunable impedance to control. Now, beyond beamforming, we have no idea what actually having multiple layers would be beneficial, but at least from a beamforming perspective, in single user, it's sufficient to have BD-RIS. You can do BD-RIS for actual sensing. So this is an example here where actually you leverage this fancy geometry of the BD-RIS that actually increase the resolutions. For instance, your angle resolution when you do sensing. You can increase the power that is delivered on your target because of the interconnections in your BD-RIS, but you could also increase your sensitivity to angle resolution because of actually the geometry of the BD-RIS. Now, there is one more thing I want to talk about before I conclude is I mentioned at the very beginning that we have a symmetry constraint in this RIS, and this is to enable reciprocal circuit, which is simpler to implement. But BD-RIS can also enable you non-reciprocal surfaces. And so this is an example of such non-reciprocal surface. So the first one here is conventional RIS. The wave is impinging on element 1, is reflected by element 1, and you have a phase shift that is occurring while at the time of impinging. So it leads to actually a diagonal scattering matrix. Now you can have a non-reciprocal circuit where the wave is impinging on element 1 and then is reflected by element 2. The wave is impinging on element 2 and then is reflected by element 4. And that leads to actually a scattering matrix that now is not symmetric. And you see this here is not symmetric matrix. That means actually the circuit that implement this BD-RIS is actually non-reciprocal. And this can have actually additional performance benefits. And one interesting use case is when you have a full duplex systems. So think about non-reciprocity. Reciprocity is very common in communication. You'll use this all the time in TDD systems when you do channel estimation. But actually, non-reciprocity can have a benefit. And so non-reciprocity, what it means is that if a wave hits the surface from one direction, the surface will behave differently if it hits from the opposite direction. So what that means is that here, if I have a user here in orange, is transmitting a wave that is impinging on the surface, is reflected by the surface, and is received by a base station. Good. Now, if this base station is now transmitting the wave, if I have a reciprocal RIS, the wave will come back to the RIS and will be reflected into the directions of these orange users, right? But so what I can have with non-reciprocal RIS, I can have that the orange user will transmit the wave, will be reflected by the RIS to the base station, but I could have now the base station transmitting a wave that will now be reflected in a different directions than the directions than the orange users, and so directions to actually a blue user, for instance. So what that enables you to do is now to have a full duplex base station serving 2 half duplex users simultaneously, and those 2 users would be located at different positions, different locations. So this is something you cannot do if you have a reciprocal RIS unless the 2 users, the downlink users and the uplink users are co-located. So this is a very interesting use case for BD-RIS, is to enable this non-reciprocity, and this non-reciprocity is only possible if you have BD-RIS. If you have conventional RIS, they will be by default reciprocal. Right, so this is actually an interesting use case for BD-RIS also, but at least to higher complexity because of non-reciprocity. So just to conclude, what we try to look at there is try to depart from these conventional architectures of having diagonal RIS and no interconnections. We want to have matrices where you exploit off-diagonal element potentially, and that enables you to have interconnections and therefore wave that flows through the entire surface. So the benefit so far is to generalize conventional diagonal RIS and star RIS kind of deployment that enables you to adjust phase and amplitude of impinging wave. that gives you additional degrees of freedom for increasing the receive power, sum rate, shaping the eigenvalue distribution, that enables you to have flexible hybrid modes or multi-sector modes. We show that we don't need all interconnection. You can have tree connected architecture that reduce the complexity dramatically. You have fewer resolution bits for each of those tunable impedance. Just one bit is sufficient. You can have more compact deployment when you have in the presence of mutual coupling, so smaller interelement spacing. You can have large gain when you have distributed element, but you have to be careful about losses. It can be an enabler of stacked intelligent meta surfaces, so for massive MIMO with just one layer of layers of BD-RIS. Can enable wireless sensing and actually can have interesting application in full duplex systems. But there are a few issues to challenge as well. The losses is important to take into account, and the overhead when you do channel estimation is also a challenge that needs to be further studied. So there are lots of additional problems that need to be looked at in terms of modeling, in terms of design, optimization, the signal processing of BD-RIS, the use cases where actually you see the highest gains, and prototyping experimentation. So far, there's been no prototype and nobody has actually demonstrated these kind of architectures. Right, so if you're interested, we have this special interest group in ComSoc. We have these best readings there. You have all the papers that in the topics are actually collected. We have tutorials and we have webinars as well. I give you some reference here, but you can find them all on the webpage, the SIG webpage. And if you're interested, you're also invited to come to Imperial on Monday and Tuesday next week, where we organize 2 workshops on one intelligent surface in analog computing for wireless communications, and one on signal processing for multifunctionals and intelligence systems. So it's also online, so feel free to connect online if you're interested. And so with this, thanks a lot to my PhD students and postdoc with whom we have worked on this actively. And if you have any questions, yeah, feel free to contact me directly by email. Thanks a lot.
Yeah, thank you, Bruno.